I'm from the company QtCore. We've got a stand outside. I'm going to talk to you all about type introspection and type unstapling in Qt. In C++, a lot of the time we talk about more and more compile-time checks. That's why people are interested in concepts. That's why people do a lot of templates and static checks like that. But there are use cases as well for removing type safety sometimes. And we'll be looking at some of those, the motivation, how it works, where it's going, and what you can do with it. A bit about me first. I am a Qt user since 2006. Been probably, like a lot of you, programming since I was a teenager, but got a bit serious about it about 6 years ago. Started doing useful things in Qt and KDE. I also contribute directly to Qt. I maintain the model view system inside of Qt. I also maintain the CMake config files inside of Qt, and I do a lot of other bits and pieces inside of Qt too. I'm also a CMake contributor since last year, so that's a very different kind of C++ compared to Qt. And I'm also interested in client tooling. About 6 months ago or so, I implemented a porting tool for porting from QtCore to Qt using Clang. So some of you who were in Jens Baller's talk yesterday, he showed some of the Clang porting APIs. So I used those to create an automatic tool that anybody can use on GitHub to do some of the boring, automatable parts of porting from Qt4 to Qt. That's also a very different kind of C++ compared to Qt. Something that's missing, of course, is Boost. I'm not a Boost expert. I've looked at it a little bit here and there, but I'm for sure interested in learning a bit more about it. I'm from Ireland, but living in Berlin, where I'm working here now. So I'm sure a lot of you are interested not only in C++, there's a whole environment and a whole ecosystem of languages out there, some of which you might want to embed into your own applications or interact with, or use as a glue between different C++ programs. We're going to talk about the C++ side of it and how we can connect those other languages. And it's not just C++ that we're interested in. As the artist says, C++ 11 is like a whole new language. And if what I've seen is anything to go by, C++ 1y is going to be as well. I have a look at the papers that are doing the rounds there, the proposals on the mailing list, and what the committee is discussing when they're meeting up. And there's 7 of them which are related to what I'm talking about here. They've got new language features, these rich pointers, which are being proposed as part of the language. They give you some introspection capabilities. There's the ANI library, that's from Boost. It's proposed as a standard library in the actual standard. The ANI library in Boost is very similar to what I'll be looking at here in the Qt variant class. Then there's also some papers about more conceptual issues, like type-in strings for C++, why they're a good idea, what's the motivation, and what's it good for. So the motivation for all of this stuff, at least in Qt, a lot of it is motivated by a desire to have language bindings, so that we can write Qt and C++ code, and we can use that in a Python environment, in a JavaScript environment, in a Ruby environment. And that brings with it some issues, because the languages are so different. Also, there's domain-specific languages. Yesterday there was a talk on embedded domain-specific languages using Boost further. And that's very different to the kind of domain-specific language that I'm talking about here. I'm talking again still about removing typesetting. If you use Boost further, you still have typesetting, which I will here have. There's also introspection and reflection concepts in what I'm showing here. The motivation for that is, first of all, tooling. Some of you have maybe been to Iceland, you've seen the gamma ray tool that's doing runtime introspection of a running Qt application. There's also testing. The Qt testing framework uses, I'm sure, so that almost any Qt class can be tested very easily by being introspective, seeing what methods it has, and automating some unit tests for that. So here's just three very common mainstream languages that you'll find out there: Python, Ruby, and JavaScript. And the big difference between these and C++ is type safety. In Python, everything is an object. Even types in Python are objects. A type in Python is an object of type type. Even type itself is an object of type type. In JavaScript, a lot of things are treated as strings, and so you have a lot of you've got very much a mismatch between what C++ expects the programmer to decide in compile time and what these languages expect the programmer to decide when they write the code. So when creating bindings or embedding one of those languages in your application, you'll have problems such as you write C++ courses and you want to process them and use them in a Python environment. So you'll be moving them to a whole different environment which does not have your include, which is not aware of your include where you define the actual class. But it's still going to be able to use it because it can do runtime type introspection on it. There's also a type to string conversion. As I said, in JavaScript, there's a lot of strings in it, everything is backed by a string. So you need to be able to, given a string, be able to create an instance of that, and also be able to determine what methods are available on a type which has that name. So you need to convert between strings and types, and you need to be able to define the capabilities of the types. That is, what properties does it have, what types are those properties. So, Python and JavaScript, they're not completely type unsafe. They do have types, but the type is only determined at runtime. So you do need to be able to know what type a certain object is and what's its base type and everything like that. Not the introspection side of it too. So one of the papers, again, like I mentioned, one of the conceptual papers about type name strings for C++ for C++1Y, probably 17. It talks about how string-based identification enables C++ to cover more use cases, such as tooling, such as language families. He says that some of the problems are currently impossible to solve without good external scaffolding. So let's look at some cool external scaffolding that is in Qt. So there's a number of different aspects to that. There's the two classes that are used at runtime in this whole API system. There's the Qt variant. Again, like I mentioned before, if any of you are familiar with Qt variant is quite similar. There's the Qt MetaType, which is a database of mappings between type streams and types, and what we call MetaType IDs and strings and types. So it's the central database of the runtime type system. Then there's the QObject and the QMetaObject. They're the basis of type introspection in Qt. So a lot of the classes that you write yourself, you inherit from QObject and you inherit from QWidget. A QMetaObject will be backing that type and provides all the type introspection. There's also compile time features which enable all of the runtime type checks and the introspection. That's based on normal C++ macros and templates. We'll be looking at some of the implementations, how they work and why they work. And then there's a third mystery part. We'll come back to that later. So first of all, we're going to look at the QVariant and the Q MetaType. QVariant is a wrapper around the C++ union. That means that the compiler ensures that there's enough space given to this thing so that I can contain any built-in C++ type. But it also has a void pointer in there, so that we're going to be able to put user-defined types into a QVariant too. Yeah. So, what's the salt and pepper kind of doing on the slides there? To think about QVariant, you can first think about a container which has the type defined at build time. So these salt and pepper canisters, the one on your left is a salt canister. You know that because it has an S on the top. Like I said, I'm coming from Ireland, where we do things a little bit differently. If we have salt and pepper canisters like this, you might not know which is in, or what complement is in which one. So this one on the left, who thinks it contains salt? Half of you. Who thinks it contains pepper? Right? See my point? So you've got a container without knowing what type it is. And what I've shown you so far about QVariant is exactly that. So it's not just the C++ union that will happen. We've also got a type defined.
What was the right answer for the
I'm sorry, what?
What's the right answer?
What's the right answer? It's debatable. There's a Wikipedia page all about it. It's all about flow versus flavor. You know, which one you want to flow faster out of it and which one you want to get more stuff out of. I think, back in the day, pepper was very expensive, so they used to put that in a wood-hole canister. But, that was 150 years ago or 200 years ago. So it is a localization issue. This thing confused me when I moved to Berlin 3 years ago. Yeah. So we bundle the data together with a label telling the user what type is contained in it. It is an integer, it's not an enum, and that's because we do allow user-defined types to be put in there. If we used an enum instead, we'd be restricting ourselves to types known by Qt itself. Who has used Qt before? Most of you. Who's used QVariant before? Most of you have used Qt. Okay. So QVariant has a lot of implicit constructors so that we can easily package something up into a QVariant. If it is a built-in C++ type, or a built-in Qt type. So you can simply assign a QString to a QVariant, and then you have a QVariant which contains a QString. So you put a QDate, QDate time, all of the value classes built into Qt have an implicit constructor in the QVariant type. For everything else, there is this static method from value, which is a templated method, which we can call with an instance. I have put in an explicit type here just to show you guys that it is a templated method, but usually you do not specify this at all. It's inferred from the argument that you pass to the method. So usually we'll just see from value my object. That's how we create QVariants. To get something back out of a QVariant, we can use some of the convenience methods. There's to int, to double, to bool, to string on the QVariant class. And that is just a convenience method around the value method. So that's the templated method which allows us to get back any type out of a QVariant, assuming we put the same type in there. So that also works for user-defined types, of course. So looking into the from value implementation and the value implementation, first we'll look at from value. It does two things. First of all, it gets the ID from the Qt MetaType System, giving it a template argument T, that's the same one we pass in, and we call this method. So this is a class, we call a static method on it, we get an integer back. That's the same int that goes into the Qt variant itself. We then use a special constructor in the Qt variant. So this is actually a private constructor to calculate the union and the type ID, the method type ID in the Qt variant, and we return that. So we will be looking more about this stuff later. Don't worry about it too much. But do take note that we see it again. So this is this question here.
Does it take ownership of the memory?
Does it take ownership of memory? I think it does a copy, right?
Okay.
Just look at it. If you take ownership or not.
Take a look at the parameter.
Yeah.
The specified value.
Ah, I see.
So you can create a copy.
Right.
Yeah, thanks.
So here again, inside of the implementation of that value method, we again call this funny static method to get the method type ID of T passed in. User type is a method which returns me the integer inside of the Qt variant, so I can match up what's being asked for with what the variant actually contains. Because if I create a Qt variant in one translation unit, pass it to another one, the other one needs to know what's inside it, and it needs to know whether it can handle that. So you'll usually have a switch statement on the other side saying, okay, well I know how to handle strings, numbers, and due date times, and customer classes. So if I'm given a Qt variant with one of those, I can extract the value from it and handle that. So the way that it extracts the value, again, is reinterpret cast what's in the unit and returns that. Otherwise, it returns the default constructor T. So the types that you put into a Qt variant, one of the restrictions that is on them is they must be default constructible. So now we're going to look at user-defined types. So we have that Qt variant class. We can put stuff in there, take stuff out, and we saw how that's done using a mapping from T to some integer type. So let's see where that mapping comes from and how to use it with user-defined types. So here I've got a customer struct. It's got some members, maybe it has some methods and some API that I've not shown. And the important part is I need to use this macro, QtCore, giving it the type name. Once I've done that, QVariant value and QVariant value will compile. If I've not used that macro, it won't compile. And also, if I get a library from somebody else and it has some types in it, and they haven't used the macro, it won't compile either. So maybe I'll have to use the macro myself. And you can get into all kinds of trouble with that if multiple different libraries try to define upstream types. But anyway, look into how it works. So it's implemented something like this, so it's simplified the macro quite a lot. But the point to see is that it's a specialization of a struct that's built into Qt called Qt MetaType ID. And remember, it has this static method Qt MetaType ID. So that's the one that we've seen before. What I've hidden in here is this thread safety. So an atomic int is actually used for these IDs. And I've hidden the logic for making sure that we only register a particular type at one time. But the thing that you need to notice is that the type is also stringified using the standard preprocessor circuit. So this QRegister MetaType method also takes the type so that we can do some checks on the type, we can create some add some flags and store them in the database with the MetaType. and it also stores the actual type name string in this runtime database. Yeah, question?
What about customer classes and namespaces?
What about customer classes in namespaces? That is also quite possible. The only thing that you need to be aware of is to use this macro outside of that namespace. So if customer was in the boost namespace, I would use QtCore MetaType boost code on the customer. So that's just fine. So QRegister MetaType, that populates my type database. And once it's populated, I'm able to use it. And the API for using that is the Qt MetaType class. So what we just saw is the Qt MetaType ID struct. That's an internal implementation detail. Now we're looking at public API. Given any ID, I can get the type name of it. Given any type name, I can get the MetaType ID of it. There's also API to construct a type, the default construct a type given a MetaType ID. So if you can imagine in Python, you might create a type, or you might create an instance of the customer type, and in the implementation of the binding in that case, the Qt MetaType API would be used to construct an instance of that particular type. Something else we have is the Qt register MetaType method. So that's similar to what we just saw, except this one does not take a string argument. All this one does is populate the database. So what we need to be aware of when using the Qt MetaType system. So, we don't rely on RTTI. We don't use type info in the type ID built into the compiler. Instead, we have our own MetaType database, and that has to be populated at runtime. So that's not populated at compile time. There needs to be some call to Qt MetaType ID T, Qt MetaType ID, to populate the database. That's important because sometimes so what we've seen so far is the Q variant from value and the Q variant value. Both of those populate the database. They make sure it's already populated. But sometimes you, for example, the Q signal spy class expects that the MetaType is already defined and in the database. So if you haven't used it with Q variant before, you need to call this method to actually populate the database at runtime. So to summarize about Q variant and Q MetaType, it's a mapping of integer type IDs and strings and actually C++ types among each other. And the strings are extracted at compile time, and the mapping is defined, populated, and available at runtime. So you can probably imagine how I could help you with further findings. Moving on a little bit, we'll look at the other two classes that I'm going to present, that's the QObject and the QMetaObject. These provide a lot of the runtime introspection features. So we'll be able to see what methods does a class have, what types do they take, what type do they return, are they public, private, protected, that kind of thing is all built into the QObject and the QMetaObject. And that's important because for tooling is a big reason for that. So a big motivation. Some of you have probably seen the gamma ray tool that we have outside that allows us to list every QObject that is in a running Qt application and change various things about the application. There's also Squish, that's a GUI testing tool made by another company, and it works in very similar ways to gamma ray and with using the same types of Qt. So runtime QObject introspection. And then we get to look at the third piece of scaffolding that I mentioned before. Many of you have used Qt before, will probably know already what it is. It's code generation. Qt ships with a tool called lock, which is one of the tools that generates code that people compile into Qt. It stands for Meta Object Compiler, and what it does is it processes a header file or a class definition, and it generates code to populate a Qt MetaType class. We'll look a little bit more about that and why it's important. It also generates some virtual methods which are overridden from the base QObject class, such as this Qt MetaType. This is the basis of signal slot connections in Qt. It's the basis of media dividing properties, which is what I'll be showing. It's also the basis of a lot of other introspection features in Qt and QObject itself. So this is what a typical Qt class might look like. Apart from inheriting from QObject, we need to use this QObject macro. In this case, I've also shown a Qt property macro. Both of these are tokens that the mock tool sees. So the mock looks for this QObject macro. When it does that, it's able to look at what class that appears on, look at what is the base class of that, look at what methods are available, what signals and slots are available, just by looking at that QObject macro. And that one also expands to a few things inside the regular C++ code as well, because the mock does some pre-processing. This one, the Qt property, expands to nothing in regular C++ code, but it's a marker for mock. And what it says is that name is a property of type QString, and I can read that property by calling the name method, which is here. I can also specify other things inside of that Qt property macro. I can say how to modify that property. I can say what signal is going to be emitted whenever that property changes, etc. But once I've done that, I can create an instance of it, and even if the pointer that I have to my instance is of type QObject star, I'm able to get the properties from the derived class using this property method. This is a method on the QObject. And it calls some virtual methods with NVI. So given a string, in this case name, the Qt MetaType virtual method will be called, and using Qt variant from value or something similar to that, it will populate a variant, return it to me, and then I can extract whatever type was returned by calling that property. So you can see probably that if this was in a different translation unit to this stuff would be in language file. So this only needs to know about the QObject API. It doesn't, my language binding doesn't need to know about the customer. And this is what it might look like. In JavaScript, you would use customer.name, and the binding implementation would do all that processing that I've just shown to variant. It would call property with the correct string, get the variant, get a value out. In the case of JavaScript, it would then convert the QString into a JavaScript string, and then that would be available in the JavaScript environment. Similar in the Python snippet, it happens that the syntax is very similar here. It's also just .name, and then we can use that Python string in our Python environment to do whatever it is we want to do in Python. You'll find that a lot of applications wish to be extendable by users. So in the same way that you can extend Excel with VBA macros, you'll find a lot of KD applications can be extended with Python. And that is using Python bindings to Qt, which works something like this. So people can write their own scripts to be executed whenever an email comes in or whatever in Python. Another thing is DSLs. This one is one that I implemented. So you can specify your own syntax for how you want to process objects and properties created from C++. So in this case, there's some curly brackets to say that I want to get a variable out using the person object, give me its name property. Also, there's this item list object, and I know that that's iterable, so I can put that in a for logic inside of my DSL. So this again is not compile time type checked, but I do of course need some runtime type checking to find out if this thing is iterable or not at all. And that's the kind of thing that you can build in and on top of the Qt infrastructure. So Q5 is just around the corner. Have a beta 2 real thing now, as we've heard already. And it's got a lot of improvements on top of what QtCore offers in this area of MetaTypes and variants and introspection. First of all, I wrote some code to make it unnecessary in a lot of cases to use QtCore MetaType at all. So that's the macro that I showed you before. It defines a specialization of a struct in Qt. But it turns out that for QObject subclasses, for Qt containers, such as the QList, the QVector, and for Qt smart pointers, such as the QShared pointer, the QScope pointer, well, actually not the QScope pointer in this case. But it turns out that for those types, we can use some schema to automatically specialize that struct that I showed you before in the macro. That's regular C++ 98 features, but it means that for any widget that we've written, we don't need to use that macro anymore. We can just use qvariant from value, it'll compile, and it'll work. Also, we can use the QList of any defined type, including ones that are automatically defined, including my own widget type, and including more complicated things. So you can have a QList, a QVector, a QShared pointer of my widget size, and that'll just work. Whether it's useful, that's a different story, but it might be useful for DSL. Another thing which I think is really cool, again, because I wrote it, is a built-in QObject class. The QObject class is a special class built into Qt. It's only for use with QObject types, and it's very similar to the dynamic class. But it does not rely on compiler feature RTTI. Instead, it relies on the generated Qt object code, which mock generates itself. So as I mentioned before, when mock runs and it finds a QObject macro, it knows the type that the macro appears on, and it knows the base class. So QObject allows us to cast up and down. So QObject cast allows us to cast up and down the inheritance hierarchy. And that's now built into the qvariant system. It's built into the qvariant.value method. So that in one translation unit, I can add a QLabel, I can put a QLabel into a qvariant, and elsewhere I can take it out as a QObject star. Of course, there's a memory here, just ignore that for the moment and assume that that pointer comes from somewhere else. But the point is that we're taking out a different type than we put in, because the C++ type system allows it. So this doesn't work with every C++ type, only QObject subclasses. And once we have it, we can again use the regular property API to get the text from the label. So QLabel, by the way, is a widget in Qt for displaying either some text or an image. Usually it's showing some text. And that text is available through the text property, because the QLabel implementation uses that QProperty macro that I showed you 2 slides ago. So I can get its text as a qvariant, convert that to a qstring, and so I can use that in my DSL. I can have that exposed in my scripting API that I published to users in Python, and people can modify and change and add new things to my own UI if that's what I'm trying to allow. But just to really show you what this means for people implementing a DSL, it just makes it so easy. So in one translation unit, I have QLabel defined, and again, memory leak, I know, but assume this QLabel pointer comes from elsewhere. I can create a QVariant type, pass that through API values, through any other translation units. In this case, I get that QVariant and I set it elsewhere. And when I set it elsewhere, I'm passing it to another translation unit where QLabel is not defined. So imagine that instead of QLabel, it's my class, some class that you've implemented in your own C++ application. All I need to do is include the QObject and the QVariant. I can get out the object star from that QVariant and access this text property. And this is already possible in QtCore, but Qt5 makes it a whole lot easier. In Qt4, when you use QVariant from value to populate this, and that's what I've omitted here as well, by the way, you do need to use that template type. So you would use QObject, QVariant from value to object star to populate that thing. But if somebody forgets to do that, then this side will just not work at all. You'll get a runtime problem. Qt5 makes it automatic. It checks whether this thing inherits from QObject using the schema, and this makes it so easy to implement it in DSL. So, just in summary about what I've shown you here, I've shown the runtime type introspection APIs in Qt. So the QVariant is the container, just like we used to any, for passing things around different APIs. I've shown you the Qt MetaType database, that is the mapping that Qt maintains at runtime for type MetaType IDs, type strings, and C++ types. I've shown you how I can be useful in language findings, tools, your own DSL, any other introspection that can be useful for you. And you've seen that runtime registration needs to be done either by calling a QVariant method or that QRegister MetaType method. I also showed the type conversions, and what I didn't really get to show was inspecting properties, signals, and slots. So given any QObject subclass, mock generates a QMeta object, which just has all the information that you could want from any type. So you can iterate over what properties are available, what methods are available, and that's of course useful again in your Python or your DSL, so you know what you can call. So, any questions? This one.
I have a question regarding QVariant. At least in version 4, the meta system was not very strong when it comes to user-defined types. As far as I recall, it wasn't possible to define if a type can do toString or the compare operator. And these things were working pretty nicely for Qt types, but when it comes to user-defined types, because it wasn't possible to register them, then those operations were not available. Are there any improvements in that area in Qt5, for example?
No, I'm afraid not. It's again something that you can add on top. In KDAB we have a library called KtTools, which does allow more useful QVariant conversions, KD variant converter or something, and that will again use schema to see if there's a toString method, or you can use a macro to say which method should be called to get the string for this type, and also it can do comparison as well, given two different QVariants, because you're right, given two variants, it does have an equals operator, but if you call that, what's actually compared is the pointers inside of that union. for user-defined types. So maybe in the run of Qt5, maybe we'll make that easier too. It's possible. Yeah.
In that code, you used when a question appeared when a variable was converted to a string variant. When the question was who owns the noun memory, I noticed that it was passed by a value. Then it's actually another value. And then you just link broadcast into void star to get it further. So it was either disappeared by now, or it was supposed to be copied later, but void star, how could that be copied? That one. Maybe just similar code, but I don't know. So T is now an array, then it's not copied, but it's just linked broadcast into void, and then it can't be copied later, but this is an array, it will disappear.
Okay, Tiago is going to answer that question for me.
Yeah, so what's happening here is that what you're not seeing is that the call to Qt MetaType ID registered a function that knows how to copy. So it actually registered the copy constructor as a helper function. So what it is doing is that it passes the pointer inside, and then it hooks up on the database where the copy is, and creates a copy, keeps the copy.
Okay. Good. Let's clarify. Does that answer the question?
Yes.
Good. So, just because I have a bit more time, another thing that is referred in Qt5 is that you almost never need to call Qt register MetaType anymore. I mentioned that when using Qt variant, we'll usually be calling a template method where T is available and the MetaType database will be populated. But now in Qt5 we make that almost not needed if you're using Qt properties. The generated code generated by mock will now register this stuff when it starts and when the type is first needed. So yeah, you almost never need to call out method anymore. Okay. So if there's no more questions, I guess we're a little bit ready.
Could you explain? Can you hear me?
Yes.
Could you explain what this Qt cast is doing if you come to the later time?
What is that's the QObject cast? So when we run mock on a class definition, we extract what the base class is, but we don't just extract a string for that. We actually add a way to store a pointer to the Qt object of the base type. So that QObject cast is at runtime it checks the Qt object of the base type when it sees what types are derived from the base type, and it's able to see if the cast will succeed, and if it will, it does a static cast. Otherwise, it returns 0. I'm not sure if that answers your question. Isn't dynamic cast doing the same? Yes, but that relies on the compiler feature, for one thing, which is not always available. And another reason is dynamic cast, yeah, well, that's about it.
Well, dynamic cast has limitations when it comes to DSO boundaries.
Right, and dynamic cast has limitations with DSO boundaries. One more question.
Is there a way, when I use Qt variant, I always use to string or something that you can also specify in template by calling value? Is there a way to get just value and to presume the one that was given, the type that was given in the start? Because we already had in type, so that would be possible.
Well, yeah, but there might also be a type conversion going on. And so the question is, if I have a Q variant, there's an integer in there which knows the meta type.
Yes.
So why, when I call .value, do I need to pass in a C++ type?
Yeah, but maybe in, I don't know, in one environment, the value was given and the type was specified, and then I get the Q variant in the other environment, and I just want, I don't know, I will say Q object star X equals Q variant dot value, but without Q object, for example.
You can't overload a C++ function on return type alone. The compiler doesn't know which function to call if the only difference is only the return type. So you need to select the return type on the typical parameter.
Okay, so it's the C++ compiler, yeah. Okay, Qt would know that, but thank you.
Okay. Thank you.